So welcome back to the post-lunch session. And the first talk we have is from Lei Yang, who's doing Mega ETH. Very happy to have worked with Lei on several projects as a collaborator. And he's presenting SALT, breaking the I/O bottleneck for blockchains.
All right. I'm very happy to be here and really honored to join this workshop. Thanks a lot for David for inviting me and for people who are organizing this this workshop. And I'll talk about this work that is actually, unfortunately, not related to consensus that we're doing at Mega ETH on unblocking blockchains from the I/O bottleneck coming from this authenticated key value storages. And this is a mouthful of a title, so based on my learning from David, the shorter the title is, the more interesting the work appears. So I'll just call it Small Authentication, Large Try. It's actually the name of the data structure. It's called SALT. So I'll just, given the expertise of the audience, I'll just spend maybe 10 seconds going through this slide. It just talks about what is an authenticated key value storage, right? It's just a Merkle tree. And yeah, it's really frustrating that there are many different names of this primitive. Someone calls it AKVS, someone calls it authenticated databases, someone calls it authenticated dictionaries, but we're gonna just stick with an AKVS in this talk. So what's nice about AKVS is that you have this commitment which you can use for, say, state settlements from layer 2s to layer 1s, light clients if people are still interested in this kind of stuff, and all sorts of interesting stuff, like for example, cross-chain transfers, right? You need to prove that something has happened or some state is true as of some block in chain 1 to chain B, so that you can, say, move money between the chains. But what's really sad is that maintaining those state commitments or updating those AKVSs when you update the underlying state is actually pretty costly. So what you're looking at here is a bunch of benchmarks we did. On the x-axis, we vary the amount of memory available to a Rust Ethereum execution client when it's running through, I think, 100K Ethereum blocks, mainnet blocks. And on the y-axis, you're seeing a breakdown of the time it spends executing those blocks. So it's pretty unfortunate that across the board, you are seeing that updating this AKVS taking almost 5.8 times to almost 10 times longer than just running through the transaction. So it's pretty funny, right? You spend, say, 1 second executing transactions, computing everyone's balance. You spend 10 seconds updating the Merkle tree. And it's killing the performance of execution client. And that's kind of the motivation of this talk. And the reason that we know that Merkle producer tries are the data structures that Ethereum uses as AKVS. So the reason that they are really slow to update is because we know in MPT data structure, each node is the hash of its children. And when you update a particular key, the thing you do is that each path in this Merkle Patricia trie also represents like a snippet, like a segment of the key, right? So you chase the correct edges until you find the key that you're looking for example, 8 bad food, right? And then when you update the value, the key value pair, you have to really trace it back to the root to update all the nodes that you have touched. And it's these random disk IOs, because these nodes, they all sit somewhere on the disk. You actually cannot predict the path that you're going to access. So it's those random disk IOs that kill throughput. It's actually killing throughput, not just latency, because modern SSDs, they are much, much more efficient when you give it like a very regular serial work to work with instead of just throwing random probes here and there, right? And on the other hand, MPTs are actually kind of nice. They have some very interesting properties. One of them is they are history independent in the sense that the shape, the like internal construction of the MPTs only depend on the currently stored key value pairs, not the history through which those key value pairs end up being there, right? It's not dependent on the insertion deletion history. It's only about the current thing that you're storing. It's a very nice function of what you're storing here. So what it enables first, it enables straightforward and succinct non-membership proofs. Non-membership proof basically says that you want to prove that something does not exist in the AKVS. And also, it's very easy to reconstruct in the case that the AKVS is lost, or in case that you are like synchronizing with a node. It's very easy to reconstruct the AKVS because you only need to get the leaves. You only need to get the key value pairs. You can do whatever you want locally instead of having to follow the history through which the data structure is constructed, right? And also, it's a pretty subjective matter, but having the data structure being a function of the content it stores is a pretty elegant feature. And also, by the way, MPTs, they also have very, very modest resource consumptions because it's just computing a bunch of hashes. So our wish list, sorry. Yeah, of course.
With regard to the previous slide, is this copy on right, or are you updating in place?
We are updating them in place. But same goes for copy on write, which can be even more random, the workload.
But the write workload would then not be random.
Yeah, exactly. The write would not be random, but then afterwards the read will be random. Yeah, so either way, yes. Thanks for the question. So our wish list, okay, so we want to preserve the two nice properties of MPTs, and we also want to minimize disk I/O, which is what's killing us for performance. So a crazy idea here is, what if we just throw the entire AKVS? Of course, we're not crazy enough to also say that we want to throw the actual key value pairs into the system, into the memory. But what if we can just fit the entire trie, the upper side of the trie, like the authenticators, to the memory? So then it's basically incurring 0 disk IOs. It's like cheating, but it's also pretty practical. So in order to judge if we can actually do that, the very interesting metric we have to look here is what we can call storage overhead or storage efficiency, right? It's the size of the trie, not including the actual key value pairs, divided by the number of key value pairs that you want to authenticate to, right? It's basically the per key cost for it to be committed to, right? So again, let's look at MPT. In MPT, we use a radix of 16. Here, radix parameter R tells you how many children, at most, a node can have. Suppose that there are n key value pairs, then in the ideal case, because we know that a node can have at most 16 children or R children. So one layer above the leaves, or one layer above the key value pairs, you are looking at at the minimum n over R nodes. And it goes on to the root. So if you add this series together, you are at n over R minus 1 in total. And that translates to 2.13 bytes per key. And we are assuming 32-byte SHA-256 hashes. And that's about 3.2 gigabytes for 1.5 billion keys, which is kind of a reasoned metric, a reasoned measurement of the Ethereum blockchain. So it looks pretty nice, right? But however, it's a pretty unrealistic assumption. And especially the unrealistic assumption is that we're assuming that every node, every internal node of the trie is having all of its potential 16 children filled up. We're basically assuming a complete regular tree, which is the dream of computer scientists, but it usually rarely happens in the real world. And the reason that it does not really happen in the real world is about key sparsity. It's about like the sparsity, especially down here. And it's because, remember that there is some meaning about the path through which you trace from the root to a particular node, right? For example, here, this node, the entire subtree of this node share the same prefix of the key, which is 0xDAD. And here, if you go one step further to this node, then it's actually DAD B, right? So the deeper you go, the longer the prefix, the longer the shared prefix you are assuming. And you only have so many keys in your system. So if you go deeper and deeper, the number of children or the suitable keys you can find for a node is becoming fewer and fewer, and at some point it will just stop filling up all of its 16 possible children. So that's the logic flow. basically, the deeper the node goes, the fewer keys it has, and the more underutilized it is. And the underutilization basically means that we have to find other we have to find other nodes to provide for the capacities which it's not providing, right? And here is some analysis. So we have some experiments showing that this analysis is kind of correct. We're kind of approximating a non-memoryless process using a memoryless process. So it's at small, relatively small arity. It's not that accurate, but it's fine. So here, the blue curve is the real radix trie, 16 array, and it's basically taking about 16.8 gigabytes for the same 1.5 billion keys workload that was mentioned. So it's several times higher than the ideal case, right? So it's just one example. So currently, so as of now, we know that, okay, so we really need to reduce the size of the trie because 6.8 gigabytes, not even including any other metadata that you need to store, is not really realistic for, say, a low-end laptop to run an Ethereum client. So we need to keep shrinking the size of the tree. And one idea is that what if we just increase the arity of the tree? Because as you increase the arity of a tree, it flattens the tree and also it reduces the number of nodes. So would we just do that? And it's actually considered by, say, Merkle tries, which Ethereum considered to be a replacement of Merkle Patricia. I think the plan is scrapped, but I think they were considering R equal to 256 radix, and or there are databases that are optimized for Merkle Patricia tries that are trying to pack a small subtree into a 4 kilobyte page on a modern SSD, just to like make use of the unused I/O bandwidth. So, but unfortunately, these methods also don't work because as you increase the arity, it also increases sparsity. So it kind of cancels the effect. And this is one example. If you use 256 array, yeah, it works better, but still much worse than the theoretical optimum, which is complete trees. And actually, you can also do some theoretical analysis, and you can see that even if you keep increasing arity, at some point it saturates, which is actually quite interesting. The purple curve is the average overhead, averaged over trie sizes, and the shaded area is the worst and the best storage efficiency. And you can see that the best is kind of decreasing, but it's not decreasing as fast as the optimal case, and the worst and the average cases just stay here. And this is like a same figure zoomed out, so it's really converging here. Okay, so quick recap, we want to minimize disk I/O, and our crazy idea is to fit the entire authenticated, the entire authentication data structure in memory. But the problem is we want to really minimize the size of the tree so that we can fit as many key value pairs as possible given a finite amount of memory, right? And we saw the challenge, which is that radix tries, which are, say, MPTs or Merkle tries, they are sparse, especially towards the bottom, and they are inefficient. They are storage inefficient. So an insight here is that actually, even though the entire tree, when you look at it as a whole, it's inefficient because of sparsity, not the entire tree. It's actually not like it's not homogeneous across the board, right? What you can do is to like break down a normal radix trie by levels. So for example, here I'm showing in blue shaded area the first 4 levels of the trie, and the orange area the remaining levels. And after a certain point, the first 4 levels are actually filled up. You can see that the contribution of the blue part dies down. It only makes sense, right? You cannot fit an infinite number of key value pairs within a finite number of levels. So the insight here is that if you are willing to just use the trie for some certain number of, at least some certain number of key value pairs, the first few levels becomes very efficient. They are kind of converged to complete trees. So that's kind of the insight that we're taking here. And that basically says that an optimal data structure should be heterogeneous in the sense that the first few layers, they are going to be complete anyway, even if you just do our normal radix trie. So you just take it and just do a static complete tree just force it to be a complete tree, right? Just because you're not really wasting too much space. It's almost complete. It's almost guaranteed to be complete. On the other hand, the bottom layers, as we saw, they are pretty sparse. And when they are sparse, you cannot really afford to construct indexes over those sparse trees anymore because you are just throwing a lot of internal nodes for just a few key value pairs. So what you should do is to flatten them, flatten each subtree into a flat open addressed vector or hash tables, depending on how you want to provide random access into those buckets. So again, you want a static main trie, which is almost guaranteed to be complete, so you don't really lose that much efficiency here, and a series of dynamic buckets that can deal with the sparsity of the key space. So this is kind of the main idea of sort. In sort, there is a main trie, as I mentioned. It's D levels, D is a parameter of complete R array tree. And here, each node in this tree is the vector commitment of its children, right? And the nice thing about being a complete tree is that it can be packed into an array. So no need to store pointers, so it minimizes the space cost. It's very easy to implement. The code is very clean, and also its parallel updates to this trie is very easy. I'll skip what is vector commitment. And OK, so below the main tries, you have buckets. Each leaf of the main trie corresponds to one bucket. So here, basically, we have R to the power of D minus 1 buckets, because there are R to the power of D minus 1 leaf nodes of the main trie. And each bucket is a vector, but the way you manage the vector, because you also want some pretty efficient random access into it, you manage it as a strongly history-independent hash table. And the fact is it's flat, as I mentioned, it's always space efficient. It's just one vector commitment over the entire content of the bucket. No intermediate nodes to deal with, always just one vector commitment, always the same constant storage overhead. And the SHI property makes sure that the entire data structure is also history independent, which is what we want. So I'll walk you through the insertion process. First, we find the bucket, and it's exactly what you would expect. You first hash the key of your entry into something hopefully uniform, and you take a mod over R to the power of D minus 1, which is the number of buckets, right? And that's the bucket you should be looking at. And then you just perform your normal insertion process into this SHI table. And after you insert, you will find that your key is inserted into some particular index into this vector, and that's your so-called bucket slot. And a sort key basically uniquely identifies a particular position in this data structure. Is like a combination of the bucket ID and the bucket slot. And then, of course, you have to propagate back the vector commitments all the way up to the to the root. And we use we use inner product arguments for vector commitments. OK, so there's actually something interesting that you also can do with this data structure, which is decouple authentication and storage. And this is what it is, right? So the observation here is that we've mentioned that we want to use SHI tables to manage those buckets, but actually they only need to exist in your imagination, right? It just defines, given a bunch of key value pairs that you have inserted that exists in this vector, what's the representation, what's the arrangement of those key value pairs when you want to compute the vector commitment? It's just for dictating how you should compute the vector commitments over a bunch of key value pairs. This is not about dictating the physical layout of the key value pairs. So what you can do is you can just throw in whatever, say RocksDB, LevelDB, any key value storage, and store the mapping from sort key to actual key value pairs. And that's it. So of course, this key value storage exists on the disk. The overhead is really small. In addition to the key value pairs, it's only 4 bytes of extra data for the sort key, for the key to the key value storage. And of course, the main trie, as we designed, we want to fit it in the main memory. So it's r to the power of d minus 1. Leaves is actually not r to the power of d minus 1. It's a series. But on that order, times 64 bytes per node. We're using IPA. And that's it. So the bucket exists in your imagination. Does not really need to exist physically. So there are some caveats. One is that if you modify, it's always in place. But if you insert or delete into the SHI table, of course, you sometimes have to move around existing items just to keep the SHI invariant. So sometimes you have to move around extra keys. But turns out that the constants is not an issue in practice. And also, what if you run out of space? It's fine. You can just add more segments, and you can also compute. You can also construct a tiny complete trie just for a particular bucket, because now it consists of multiple segments, right? It's easy. And membership proof, you just do a SHI table lookup and open the vector commitments. And non-membership proof, you also do an SHI table lookup. But it's basically what happens when you want to probe into a key that does not exist in your hash table, right? You basically what you do is search until you find an empty slot. So you kind of open all the slots that you've hit, including the first empty slot you have hit in a failed search in a hash table. And you open all of those in vector commitments. OK, so some analysis. We use R equal to 256, D equal to 4, and 64 byte vector commitments. And the main trie is about 16 million nodes. And that's about 1 gigabyte of memory footprint. And each bucket initially was also set at 256 slots. So all in all, it authenticates to about 4.3 billion key value pairs, which is about 3 times the size of a current day Ethereum blockchain, and that translates to about 0.25 byte per key value pair authenticated to. And the overhead stays below 0.5 byte per key, even if you start expanding those buckets, and it eventually converges to 0.25. And this is the comparison with all the schemes we have talked about, and you can see that sort actually converges very closely to the theoretical optimum, because, yeah. OK, so I/O cost always 0, and in terms of the main trie, which sits in the memory, to the buckets, of course, you have to update the underlying key value storage, but it's something that you have to do when you execute blockchain transactions anyway. It's totally separated from the authentication data structure. And as I mentioned, during insertion deletion, probably more, but turns out that when the load factor of the SHI tables are not crazy, it's not too much. Computation cost, we're using vector commitments, so it's definitely much more expensive than just computing hashes, about 20 times more expensive than Keychack 256. But we did some experiments. What's nice is that it's actually pretty parallelizable. So at 1 core, you can do 45,000 keys per second. Again, it's totally compute bound, right? There's no I/O happening. It's only about computing those IPA updates. And we're using a desktop CPU. It's about $500. So finally, some comparisons with other state-of-the-art constructions. First, NOMT, near optimal Merkle trie. It's basically a binary Merkle trie, but with nodes packed into 4 KB pages for fitness on more than SSDs. And also QMDB, it's basically packing a journal, basically the updates and deletions to your key value storage into a Merkle mountain range with garbage collection. And we're assuming that we're running the hybrid mode, which uses about the same amount of memory as SOT and NOMT. So benchmark numbers, SOT can do about 87K updates per second. I know it's different from the number I showed before. We did some updates. It's from a new experiment, new code. And QMDB about 63K, and NOMT about 40K. Disk space amplification, very small for SOT. NOMT, we're not sure. We didn't run experiments. QMDB, because it's garbage collected, it's basically a trade-off between amplification and your I/O. Computation overhead, definitely the highest, but it's manageable, and also it's very parallelizable. You can even use GPU. And random disk I/Os. So yeah, that's it. We talked about SOT. It's a new authenticated key value storage that scales to tens of billions of items while completely eliminating random disk IOs while being very space efficient so that you can fit the entire thing in the memory, which is the purpose. The key insight is that tries or radix tries are sparse at the bottom, so you want to flatten them into proper vectors and just use one authenticator for them. Optimal space efficiency for the in-memory stuff, it converges to complete trees, so it's pretty optimal. And the on-disk key value storage, we call it optimal because you can just use the state-of-the-art solution. We don't really dictate anything, right? You have all the flexibility. Reasonable computation cost, and it's been running live since day one of Mega ETH testnet, which we launched earlier this year in March. And yeah, feel free to check it out. Thanks. I'm ready to take questions.
You have a very nice slide where you compare the time it takes for computing the commitment versus for execution and other things.
Oh yeah.
And do you have a similar slide with SALT? Just because that was very good to understand the latency
Yes.
overheads.
So SOT, I don't have the. It's
this one, yeah.
Yeah, exactly. It's very labor intensive to run this experiment. So we didn't, but we have a qualitative answer, which is once we move to SOT, disk I/O is. We also test the disk I/O like bottleneck, but it's 3 times higher than what the EVM execution bottleneck is. So we have like a 3x runway before we run into disk I/O issue again. But then, even then, it's going to be key value storage access when you run those transactions, not when you are updating those commitments.
So you're not gonna hit this on the update.
At least for update commitment, it's fully disentangled from I/O, and it's all about computation now. So you just throw in more CPU cores.
Okay, thank you.
Yeah. Very soon. We hope to get to mainnet. Fingers crossed. Yeah.
But the testnet code isn't available.
It's not available yet, but we are actually preparing for audit, so it's shaping up. Yeah, it'll be available. Yeah.
Can it connect?
Yeah, of course.
Does it work for adversarial updates and key access?
Very good question. Yes. So there are at least two types of attacks. One is you try to increase the size of a particular bucket too much, and for that we just rely on economic incentives. So we assume that as you expand the bucket, at least once you start to increase the insertion cost into that bucket. Yeah. And the other type is you can create pathological cases in particular hash tables, but that you can just use rehashes. You can add a nonce here, and once you're unhappy about the state of the hash table, you rehash it, you shuffle it. Yeah. Dalia.
Maybe in the interest of time, we can take questions.
Of course.
Thank you very much, Lei. And the next talk is Autobahn, presented by Professor Natacha Crooks from UC Berkeley.
Thank you. So this morning it was the Berkeley coffee that didn't arrive, and now it's the Berkeley laptop that can't connect to the Berkeley projector, so I concede Stanford wins. But with that, so very excited to be here and very excited to tell you about our project, Autobahn, which is a new Byzantine fault-tolerant consensus protocol that we published at SOSP last fall and that we've seen some sort of recent adoption in industry. Now, for those of you who don't know, Autobahn is the German word for highway. So the German highway famously has no speed limit. So when you think of Autobahn, I'd encourage you to think of a Ferrari going 200 miles per hour on the German highway and not on the Berkeley-Stanford congestion stretch. So with that, at a high level, Autobahn really strives to do 2 things. The first is that we aim to build a system that accounts for more realistic network conditions. So something that offers high performance, both when the network is behaving well, behaves gracefully, but also when it recovers from intermittent turbulence. And what we found is that networks tend to not be super well behaved in general. They're often quite blippy. The second is that we'll obviously make the case that thinking about BFT consensus doesn't need to be a dark art, and I'm sure you all agree with that, and that it can be simple. And that's paramount for building systems in production. Now, what I find funny about introducing this line is that the next 3 talks are also going to claim to have a protocol that is simple. So I'm going to say this is simple for my definition of simple. So let me, before we get started, let me briefly set the stage. So I don't think BFT needs a huge amount of motivation for this audience. So very quickly, just to clarify what I'm talking about, BFT consensus is at the heart of the blockchain stack and promises to implement the abstraction of a shared, totally ordered ledger, meaning that every participant orders the same set of operations and does so in the same order. And these guarantees hold even if a subset of participants misbehave. Here we're talking about n participants and f possibly arbitrary faulty nodes. Nothing special here. So BFT consensus has a hard job. It's a really nice abstraction to have, but you need to implement it well. And for it to be useful, it needs to have high throughput, it needs to have low latency, and obviously, as the name suggests, it needs to actually tolerate Byzantine faults. Namely, it needs to be robust to arbitrary network failures. And you have to do this while dealing with the troubling reality that our networking colleagues haven't yet figured out how to make the network synchronous. And famously, consensus is impossible in an asynchronous network. But obviously, that would make for a very short talk. So what do we do? Well, to deal with this, practical solutions that are deployed today look to partial synchrony. So in this model, we basically use timeouts to approximate synchronous intervals and try to detect faults. So we're going to maintain safety at all times, but we're only going to offer liveness when synchrony eventually holds. And in BFT theory, this is typically modeled as something called the global stabilization time, or GST. And this is basically the period after which timeouts start holding. And now this model allows us to rigorously talk about what a protocol does, but obviously there's a big gap between the bookish version, where there is a point at which GST will hold forever, and what we deployed in practice. And current systems have to deal with the practical reality today. So in practice, this rosy reality of ever holding synchrony is of course a fiction. And, current protocols recognize that. Missed timeouts are common and can trigger for huge kind of behaviors, ranging from DDoS to network delays to simple replica failure. Now, the cause of those events doesn't necessarily matter for our use case, so I'm going to bundle them under the umbrella of something called a blip. Now, a blip is anything that temporarily interrupts the progress of consensus and requires us to take action to recover. Now, something that I want to emphasize here is that these blips aren't fringe cases. Instead, as the name partial synchrony suggests, blips are the common case because synchrony is truly partial or periodic. And this means that to claim good performance, a partially synchronous system needs to perform well both in the absence of blips as well as during their resolution. And this is really the problem that we're going to target today. So existing systems don't handle this disconnect super well. So if we take a simple experiment with Hotsoft, one of the most popular BFT protocols today, we're going to simulate a blip caused by a single replica failure. And we're going to run the experiment with this fixed input rate close to the system peak throughput. And the graph is going to show latency relative to its start time. So, latency of transaction commit relative to its start time. So during the blip, Hotsoft is going to make no progress, and as a result, the incoming requests are going to form a backlog. Once the blip resolves and the progress resumes, this backlog needs to be worked off. But you can only do so, you can only work off this backlog as much as the excess resource capacity allows you to do so. And this is going to result into a performance degradation that is actually going to last well beyond the resolution of the initial blip. And we're going to call this problem a hangover. This is the effect of trying to recover from a blip. Now, I think everyone's going to agree that hangovers, whether it's in real life or in consensus protocols, are undesirable and we want to avoid them. And ideally, we'd like to tolerate a blip very much like this. During the blip, we're going to continue to lose progress. That means that transaction latency is going to increase. But once the blip ends, we're going to immediately make up for all lost throughput and return latency to normal. Now, we're going to call protocols that achieve this property seamless. a seamless partially synchronous protocol should fully avoid hangovers, and perhaps obviously it should do so without cheating and simply killing liveness altogether. So in particular, we're going to want to develop seamless protocols that do not produce more blips in the process, because otherwise that defeats the point. So on that note, let me introduce Autobahn, which promises to satisfy all the sort of tough demands that we expect from BFD, as well as seamlessness. Autobahn wants to achieve high throughput, low end-to-end latency, and seamless recovery from blips. And an orthogonal goal that we pursued while looking at Autobahn was that we wanted the design to be not just simple, but also modular, meaning that you can actually plug in your favorite BFT protocol in Autobahn's architecture to give it high throughput and makes it seamless. So for whatever reason you're currently deploying hot stuff, for example, you can combine hot stuff with Autobahn to add seamlessness to hot stuff, or replace hot stuff by any BFT protocol you choose. So let me talk about how we do this. At a high level, Autobahn is going to consist of two core components. The first is going to be a data layer that transports batches of transactions at the pace of the network, regardless of interruptions to consensus. And the second is the consensus layer that is going to consume this data layer and reach agreement on its output. Now, separating the data layer from the consensus layer is a well-known idea, and that's not the main contribution of our system. Rather, our challenge lies in finding the right balance and coordination between the two layers. If we offer too few guarantees, then we'll end up with something that is not more seamless than any existing protocols. But if we lump them together, then this is going to come at a significant performance cost. So we really wanted to find the right balance and the right level of interplay between the data layer and the consensus layer to achieve seamlessness, while preserving high throughput and low latency. So what we settled on is that to support seamlessness, our data layer needs to have three key properties. So first, we obviously need to make sure that our data can be reliably retrieved. And that requires us to ensure that at least one correct replica has stored the data. Otherwise, Byzantine replicas can cause us never to recover the data. That's not surprising. In order to avoid hangovers, we also want data dissemination to make as much progress as possible, namely at the pace of the network. And I'm going to call this property responsive data dissemination. And finally, we want to be able to easily index or disseminate data so that arbitrarily, independently of the amount of data that has accumulated and has been disseminated, consensus can easily index it and order it all at once. So that's the three properties that we're going to want from this data dissemination layer. Availability, responsive dissemination, meaning that you make progress at the speed of the network always, and this instance referencing property that consensus is going to use to quickly recover from blips. So let's start at the top. The key unit in Autobahn's data layer is a car, which is just a fun way of describing the process of guaranteeing the availability of requests. A car starts with one replica that acts as the proposer, and that proposer is going to broadcast a batch of transactions to everyone in the system. Other replicas are going to store this batch and return a vote to acknowledge that they have stored the data. Once the proposer receives enough votes to ensure that at least one correct replica has stored the batch, it can prove to others using this car certificate that this batch is truly available. Nothing fancy going on here. One thing to highlight, though, is that cars do not provide any stronger guarantees than data availability. Specifically, it is possible for cars to equivocate. That's okay. And the reason for why that's okay is the data layer should be concerned about dissemination, not ordering. What this does is guarantee the data availability, and that keeps the decoupling between consensus and data dissemination very clean. Now, once we have cars, we're going to change them together, just as others have done in the past, into what we call a lane. Specifically, each new car that a proposer creates is going to contain a hash reference to the previous car it created, which implicitly is going to create a total order within a lane. Now, this chaining property is going to allow us to uniquely identify and prove the availability of the entire lane with just the last car. And this is what gives us our instance referencing property. Specifically, because you're including the set of hash references, as long as you have the final tip of the lane, then you know that all previous blocks that were in that lane are also available. And that will give us our instance referencing property. And we care about it because of seamlessness, because we're going to leverage that property to allow consensus to commit long lanes very fast with just using the first car. And we can do so at a cost independent of the length of a lane. Finally, we're going to take the concept of a single lane and expand it so that every replica governs its own lane. Specifically, each lane is going to grow independently of other lanes and without timeouts. Now, having multiple lanes maximizes the throughput and guarantees that dissemination does not hinge on a single proposer. And because that's a problem, because that single proposer might be malicious. Running them independently is then going to minimize coordination and allow us to have flexible proposer speeds, which can be good if you have heterogeneous validators, for example. Now, lanes guarantee a responsive dissemination property, and we care about this seamlessness because we're going to continue growing our lanes even when consensus cannot make progress, as long as data can still go through. Now, usually we get a question here that says, well, what if there's a network partition and data can't go through? Well, there's nothing we can do here. But what we found is that during blips, there's often cases where data can make it through, and there's a progress interruption because of a leader failure, or because there's a partition that doesn't partition the network fully in the middle. So there's a lot of cases where data is still being disseminated, it's just consensus cannot make progress. Okay, so this is how we structure our data dissemination layer. Now we can move on to consensus. So let's first try let's just take a look as to why we even still need consensus. Well, remember that our data layer only provides fairly weak guarantees. And that means that asynchrony or equivocation can cause lane states to diverge between replicas. For example, two replicas here, they don't need to necessarily have the same lane state. So specifically, if you look at the third lane here, replica 1 has 2 blue cars, while replica 2 has nothing. In contrast, if you look at the orange lane at the very bottom, the first replica has seen 4 cars, while the right replica has seen 3 cars and a truck. And that can happen because our lanes, by design, do not guarantee non-equivocation. So we need consensus to be able to reconcile divergent lane state. And this is where the instance referencing property is going to come in handy. So remember that because of instance referencing property, we can uniquely identify an entire lane from just the last car alone. So instead of reaching agreement on cars individually, we're simply going to propose a snapshot of our data layer by using the last car, or the tip, of every lane. So in the example here, the snapshot would be, the tip cut would be green car 2, red car 2, blue car 2, and orange car 3. And this simple tip cut is going to transitively prove the availability of all preceding cars. And in particular, this means that the size of our consensus protocol is going to grow as a function of the number of lanes, but is going to be always independent of the size of the backlog, which is vital for guaranteeing seamlessness, because that's what we want to immediately commit any backlog data that arose during a blip. So tips give us succinct snapshots, and that's great. Now let's just say that we propose this tip cut here. So the obvious question is, when should you create new tip cuts? Now ultimately, consensus works on data. There's no point in doing consensus on data that you don't have. And so we're always going to want to make sure that we do a new consensus instance when there's new data to propose. Now, obviously, because some lanes might be malicious up to F, we don't want to wait for all lanes to have new data. So the halfway point that we found is that we're going to propose new tip cuts when you have n minus f lanes that have new information. Why n minus f? Because this guarantees that a majority of new data comes from honest proposals. But this is configurable. You can you can configure it to account for different bandwidth between lanes, reputation schemes, so on and so forth. And we have lots more details about that on the paper. So you'll notice that I'm slowly running out of time, and I haven't mentioned how we reach agreement. Now, I'd love to sort of tell you more about the specific protocol that we use, but I don't have time to go into details. So learning about it is one of the many pleasures you'll get by reading our paper, hopefully, or the many headaches, depending. But you can very much think of it as a pretty standard PBFT protocol. We have an option for it to be linear, so like SBFT, or we can be quadratic, like PBFT. And what I want to point out instead is a couple of sort of features that I find cool. The first is that our data synchronization subprotocol takes advantage of our lane structure to provide the guarantee that you can fetch missing data in just a single round trip. Now, obviously, if you have to download 10 gigabytes of data, that's still going to be slow, but you can identify where the data is in a single round trip. The second benefit that we have is that there's a number of additional optimizations that we do to minimize latency. So this includes, amongst other things, a commit fast path and pipelining, such that when you take the quadratic version of the consensus protocol, we can have optimal message latency. So we can have 3 message delays in the good case when you have the fast path, and 4 message delays when you go slow path. Add a couple of extra message delays if you want the linear version of PBFT. And the last aspect is that just because I'm saying you can switch PBFT and from linear PBFT to quadratic PBFT, we can actually keep the system modular, meaning that we can instantiate the Autobahn framework with multiple consensus protocols. So you can use the same lane structure and run PBFT. You can use the same structure and run SBFT or others. And that was by design. We wanted to very much separate the data dissemination layer from the act of agreeing on tip cuts. The last aspect is execution, and that's nothing very challenging here. So once a tip cut becomes committed, replicas can commit and order all cars and the transactions that precede the tip cut. So how do you order the cars? Well, that's not a very hard thing. Because everyone agrees on the same tip cut, that you can use any deterministic function to interleave the various lanes with respect to each other, come to the conclusion of the same total order, and then execute it. You can execute it using the whatever execute engine you might want. So before I end, just want to show you some brief experimental results. So we evaluated Autobahn against protocols in 2 categories. So the first is, I would say, the traditional star BFT protocols, like Hotstar, for example. So they have really good latency, but they do not separate data dissemination from consensus, and as a result, as we showed already, they struggle with seamlessness. We also evaluated a variant of Hotstuff that tries to naively separate data dissemination from consensus, but this design also doesn't guarantee seamlessness. Now, I'll call those vanilla Hotstuff and batch Hotstuff, respectively. The second class of protocols that we looked at is Bullshark, and that's a state-of-the-art protocol for achieving high throughput specifically, and it sort of descends from the family of DAG BFT protocols that have become popular in recent years. And those are almost seamless, but not quite, and I'll leave that as an asterisk. Feel free to, we can discuss this offline, but from the point of view of this talk, I'll just consider them as seamless. And those achieve high throughput, but struggle with achieving good latency. So onto the numbers. For our first experiment, we showed a throughput latency graph. And we do this in an ideal fault-free scenario. So a throughput latency graph, for those of you unfamiliar, works like this. You increase the number of clients. This increases the throughput that your system has, which is what's going up on the right. And at some point, you're going to hit saturation, which is going to cause latency to spike up. And so the number that matters is the number before latency starts to spike up, which is the peak throughput that you can get, and that's the latency that you'll have under stable conditions. So Autobahn, shown in green, is able to match the throughput of Bullshark, shown in blue, while also having latency that is comparable to Hotstuff. And compared to Bullshark, this means that Autobahn's latency is over 2 times better without making sacrifices in terms of throughput. Most importantly, Autobahn's pitch was not just about performance, but it was really about recovery from blips. And since we already showed you that how hot stuff deals with a replica failure earlier, let's just quickly revisit this example with Autobahn. So we had a leader failure. We increased the blip duration slightly, but the takeaway remains the same. Hot stuff in blue is going to suffer from a significant hangover, which is even longer than the blip duration, because it did not optimize for seamlessness. In contrast, Autobahn, shown in orange, returns to the base slice latency immediately as promised, aka immediately as the blip ends. And so we are able to achieve seamlessness. So that brings us to the end of sort of the Autobahn overview. So I want to briefly summarize. So Autobahn shows us how to build a BFT system that is not just efficient under partial synchrony, in theory, but also in practice. It matches performance of existing BFT protocols, but has much better robustness. And what we like is that it's simple, meaning that you don't need to start from scratch, but you can already build around the core that you already have. Now, Autobahn has been adopted in production by a number of companies, which we're pretty excited about. Say Commonwealth Older Broadcast, Beharvest, Inform Insomnia Chain, Hiller. So if you're thinking about what consensus protocol to pick, we'd love to chat, and we'd love to see how we can motorize your existing consensus protocol rather than tell you how to replace your existing consensus protocol. So if you have any questions, we'd love to chat more. Neil, who is one of the lead PhD authors, is in the room here. Florian is available remotely. If you don't have any questions, but you want to give Neil an academic job or an industrial research job, just talk to him anyways. But thank you.
So if you're waiting for every lane to have at least one new transaction before you do a cut, couldn't this get inefficient if some of the replicas either don't have new transactions to offer, or if they're all offering the same transactions, so you have a huge amount of redundancy across the lanes?
I think at the end of the day, there's two issues. There's the issues of duplicate transactions that we don't solve, and as far as I know, that's a problem in most systems unless you try to, before submitting the transaction, do some amount of deduplication. That is a problem here. The second part of the question is this is configurable. So it is perfectly fine to say that I'm going to do consensus every k unit of time, and that is going to confirm that the lack of progress is important. You can do it optimistically if you think that you trust the lanes have been reputable, and you can do it as soon as you have one more element. It's a completely configurable parameter, so whatever works for your system.
For the car, to chain it, do you have to give the certificates of the last one back to the next people to verify that and then give you attestation back, or how does that work?
Yeah, so the proposals includes the
proposer includes the last certificate.
Yes.
To the next proposal.
So each lane is one validator, and so when you do when you create a car, you include a reference to the previous car, and the certificate that you have from the previous car.
I see. Thank you.
I'm just wondering if there's any particular reason that you didn't choose to compare with dispersed ledger that has the same idea of separating data dissemination using VID from consensus, making it leaderless so that each node can disseminate its own data, and also I think the lane aggregation idea, which is basically for each person to disseminate their own data, but having a consensus only for agreeing on progress across the board, like the envelope of dissemination progress. I think the only difference I perceive, since I'm a co-author, is that dispersed ledger is in the asynchrony setting.
Yeah, so it's a fast-moving space, and so we try to do a good job by comparing against representative style protocols. Specifically, that's why we picked Hot Stuff on one and Bullshark on the other. I also think it was very, if I remember correctly, almost concurrent work, so we didn't have the thing available.
SDI 2022.
Yeah, so I think by the time that we were building Autobahn, it was like this. And I think we made the decision to just have partially synchronous protocols as a way to make a clean cut.
Makes sense.
All right, maybe we can postpone the remaining questions. We thank you very much, Natacha, first of all. After this, we have another session with 3 talks on high throughput protocols, so you'll have a lot of questions to ask about high throughput and comparing protocols to each other and so on. We'll start the next session in half an hour, so 3:30 we'll start.